Okay, so I have solved all four problems, so let's go through them. So the first problem, so here we are given a string S which contain digits, and we have to tell if any of the adjacent two numbers have adjacent two digits have a difference of great absolute difference of greater than 2 or not. So so this is just a simple idea. So if we check the absolute difference, like in Rust I have this abs for method for absolute difference, but it's the same thing. So we take the difference between two adjacent numbers. If it is greater than 2, we return false, otherwise we return 2. So this is the first problem. The second one. Okay, so here we are given three integers, and we have to tell the number of perfect kth powers in this range L to R. That means numbers which are some numbers power of k, and L are from 0 to 10 power 9, and k is 30. So the first observation is if we if we have k equal to 1, then all the numbers are there. Like every y is equal to x power 1. So every number in that range is a perfect k power. So we just take that entire range. Otherwise, let's say if k equal to 2, so the maximum best value of y we can get is square root of r, because its square will be r basically. So in even in that case, we will run like square root 10 power 9 times, which is pretty decent, like something 3 into 10 to power 4, 3 into 10 power 4. And these many iterations we can do. So yeah, a brute force will work. So yeah, if we one second. Yeah. So I didn't actually. So we'll need binary for need to powers. I actually didn't use my math module, so let's remove this. So yeah, this is my idea. If k is 1, then we all the numbers in this range are acceptable. So we take all of them. Otherwise, we start with k, and we start this x should be 0 actually. This is how I got one penalty. I thought the range L to R is from 1, but it is from 0. I missed this constraint. So yeah, we start 0 and p is the power x power k. So so we have just iterated over all the powers of k, all the kth powers, sorry, not powers of k, all the kth powers like 1 power k, 2 power k, 3 power k, and so on. So find the powers less than L, we increase the x and set p accordingly. And then to find the answer, we basically again loop over till the power is less than equal to r. We increase the answer and we increase the x and the power accordingly. Here, we need to be slightly careful of integer overflow, although it depends on the implementation detail, but yeah, we have to be careful. So LR till 10 power 9, k is 30. So we can easily have integer overflow when calculating this. So either use long or I have used a saturating power. So it will be stop this at the max value. Also, the like if we say the power function here, okay, it's not mentioned, but it generally mentions that here in my like I copied my math module because here we have binary exponentiation present here. Be sorry, because that's what we will need. But like Rust already has the if we see the power function here, so it already mentions using exponentiation while squaring. So it already uses binary exponentiation, so it's fine for me to use this function. So just an information that we need binary exponentiation here. At least I would have used it. So the internal util already uses it. Okay, third one. Yeah, this was also an implementation idea only for me. So we are given a n cross m grid, and for each element, for each non-zero element, we have to find if it is the maxima in the range. So if, let's say, at this cell we are talking about this is 2, so we go 2 rows to the left, 2 rows to the right, sorry, 2 rows and 2 call 2 oh sorry 2 rows up, 2 rows down, 2 columns left, 2 columns right. This value 5 cross 5 grid except the 4 values at the end. So we have to find a maximum in this range. If 2 is the maximum value present, then 2 is the local maxima. So that is the idea. So yeah, I this was also an implementation idea only, because if we see the constraints, the length, the matrix is n comma m, but like brute force will not work, because if we try to do brute force, then in worst case we will, like, the time complexity, we have to tell the number of maxima, so we have to iterate over each element. So n comma n multiplied by m is already there. Now if we have to see all these numbers in this range, so in the worst case it can go in another n into m. So this is 200 power 4, and generally I take the convention of 10 power 8 operations. This is 16 into 10 power 8, so this will definitely not pass. So the way the idea is I've used this a sparse table, like to find a range minimum query, range maximum query. So I iterate over, so I cannot do this, but I have just removed this one dimension. So what I've done is I go over each element, I iterate over all the rows present here, and for the maximum of this range, I have a data structure. So this sparse table gives me that idea. So for each row, I have calculated the range maximum query data structure, and then uh, and accordingly, like, I found a max across all the rows, and for each row it tells me the query in constant time. So the time complexity of this will be, this part is n square log n, because uh, basically this will be n rows and m into log m, take it this way. So n into m into log m for this part, this, and for this answer computation we are doing n into m into n. So we are iterating over each element, and then we are iterating over each row from I minus x to I plus x. Here we can see like I minus x will not go below 0 and I plus x should not exceed n minus 1. So that's handling is done here. And then one minor detail also, like if the difference between the this row and this row, the current ij and the row we are currently at, if the difference is 2, then we don't have to take the last elements. Like, if the difference is 2 here, 2 here as well for these two rows, so we don't take the first and last element. So here the right, the, like, the dj distance, basically dj distance is uh to is if the absolute difference is x, then it will be x minus 1, otherwise it is x. So for these two rows we will only get till here, but for other rows we will get all the two columns left and two columns right. Yeah, I mean that's simple implementation detail. If you know any data structure for range minimum query, this is solvable. And then if the maximum in that range is our element, then we increase the answer. So yeah, that is the third problem. Fourth one. Okay, so here we are given an array nums. We have to tell the minimum length of the subarray that is not identical to any other subarray. Identical means it doesn't appear anywhere else in as a subarray in nums. So if we see this example, let's take this one. So in this one, we this unique subarrays with length 1 are 1 and 2, but they appear multiple times. With subarrays of length 2, there are 4 options, and all 4 of them appear once. So even if one of them, we just need one of them to appear once. So 2 is our answer. And we have to tell the minimum answer. So the first observation here from the first example only is that the answer will always exist because the entire array is a unique subarray and no other subarray will appear again as the entire array. So answer will, in worst case, it will be the length of the array, but we have to tell the minimum one. So the idea is binary search here because like if it's a little maybe a little tricky to observe, but if we have x as the answer, then we definitely have x plus 1 as the answer. Like if this subarray doesn't appear anywhere, then this subarray will also not appear because like this has to appear obviously, and then we have to add another element. Like if this subarray appeared somewhere here, then including the last element, this one should have matched. Like if we see it like this. So yeah, it's a binary search idea. And to so for, I'll do binary search over length, and for each window I'll find the subarray which is unique. For that I have used the idea of hashing. So for an array hash, basically if this is a if our array is a, like a0, a1, a2 and so on till an minus 1. So I choose a prime number. I have chosen 31 in this case. I do a0 plus a1 into 31 plus a2 into 31 square and so on till an minus 1, 31 power n minus 1. This is the hash I have considered. And for each, like I've stored a prefix sum of these hashes and so on. So this is the prefix sum hash. And if I want to find hash of let's say this portion, then this will be the prefix sum, this r minus l minus 1 prefix sum till here, and then we will divide it by 31 to get a1 plus a2 into 31. So this will be the hash of a subarray if that is how we find it. So if we go to the implementation, here we stored a prefix sum of hashes. So the current number is nums of I multiplied by power of I and the prefix sum hash to consider there. And then to get hash, it is like it my prefix hash is 1 based index, so I've done r plus 1 minus l multiply inverse power of l. This is basically division by the base, the prime number. Like it's a good idea to choose this as a prime number generally. So I have to divide by this. Like if I had to do a2 plus 31 square plus a3 times 31 cube plus a4 times 31 power 4. So I'll divide it by 31 square to get the hash, and obviously after subtracting the previous portion. Then we go into binary search. Then it's a simple idea. We go binary search. We maintain the frequency of each hash appearing. So in the binary search, the window is of length m, and I iterate over all the windows, and the each hash I mean increase the frequency. So if a frequency is 1 of any of the hashes, then we return true. That means that subarray, that window of length m does not appear anywhere else in this array. So we return true. So the time complexity of this will be n log n. And this is like a not a deterministic idea. It can fail actually on some test cases. So this hashing is a probabilistic solution. We can create some test cases based, like I have chosen this base as 31, and if you notice like the values can drastically increase, so we use modular arithmetic. So uh, I have used 10 power 9 plus 9 as the modulo since it is not that commonly used. So yeah, this is the idea for the fourth one. This is like since the b and the modulo is fixed here, it can easily be hacked actually. But yeah, like I believe they wanted it like a probabilistic solution to work here, so hashing is fine. So yeah, that's it from my side. Thanks for watching. Bye.